I have considered two matrices A and B, and the size of A is m cross n, where the size of B is n cross p, and they satisfy the condition for the multiplication, and they are amenable to multiplication because the number of columns in A are equal to the number of rows in B. So they will generate a matrix with size m cross p. It will have the rows as equal to the rows of A and columns equal to the columns of P. So I have developed their general structure. The rows of matrix A um, are A11. Well, the elements of first row A11, A12, up to so on to A1n, and the last row will be AM1, AM2, up to so on up to AMN. And likewise, the elements of B in the first row are B11, B12, up to so on B1P, and the last row will be BN1, BN2, BNP. Now I would like to multiply several rows. Okay. So if I generate the entry, which is going to be C11, the first element in C, it will come from the multiplication of the first row of A and the first column of B. So if we write, it will be A11, B11 plus A12, B21. It is going to be multiplied with the first column. So it is B31 and up to so on to N. So plus so on. And finally, there will be the product that is going to be added. It will be A1N times BN1, right? So we can see there is a pattern. There is a pattern that the second index, okay, the second index is changing, right? And it goes from 1 to n. And what is n? N is the number of columns of A and number of rows of B. So, and the first index of A and the second index of B, they remain fixed. So we will confirm that after multiplying several other rows. So I can write here as the C11, where the first one, it comes from the row index of A, and the second index, it comes from the column index of B, the second matrix. So it is A1, and if I put K, and this is K1, where K varies from the first element of the matrices to the nth element, right? So likewise, if you like to confirm, let's write the other element. So if I would like to calculate an entry, for example, let's calculate the entry C12, the first row of C. Well, the element at the first row and the second entry, it will come from the first row of A and second column of B, right? So the product would be A11 B, the second column, B12, right? Plus, well, we are writing the second column of B. So this will be B22. There will be B32 and up to so on up to BN2. So B12 plus A12 times B22 plus A13 times B32 and up to so on. And finally, the last element of A in the first row will be multiplied with the last element in the second column of B. So it will be A1n times Bn2. So you can recognize the indices. You can recognize the indices that the the first index of A, it remain fixed, right, which is this one, right, throughout. And the second index of B is also fixed, right, in all the terms. So you can notice this thing. And the second index of A, which is here, and first index of B, it is varying from to 1 to 2, 3, and goes up to n, right? So this is the index which consistently move in the rows of A and the columns of B. So I can write this one as a summation. Summation A1 is fixed for the row of A, and I can write K, and then K and the second index of B that will remain fixed as the column index of B, and this K varies from 1 up to n, right? So this is the definition of C12, right? So likewise, if I consider a journal row, a journal row over here, and I call it the ith row, right? Ith row, and it is going to be multiplied with a jth column of B, right? Ith row of A and jth column of B. So let's write that one separately and explicitly. So I would like to write, well, I have a matrix A whose size is m cross n, right? So the ith row of A will have elements AI1, AI2, AI3, up to so on AI n, right? These are going to be the elements of the ith row. Now, if I write the elements of jth column of B, which is a matrix of size n cross P, so this is going to be like this. So column, jth column, so column index will remain same. So it will be B1, B1j, B2j, up to so on, and Bnj, right? So in the A row, we have n entries, and in the column of B, we have n entries, and they will be correspondingly multiplied. And what elements they are going to give us of C, right? It is the ith row of C and jth column of C. We have seen that one explicitly in the previous example. So Cij, it will come from the multiplication of ith row of A. So it is AI1, B1j plus AI2, B2j. Oh, it is not the unit vector. So j, and up to so on. The last entry in the ith row will be, ith row of A will be AIN, and there will be BN and J. And we can write by considering the second index of A and first index of B as variable to n, from 1 to n. So I can write it will be A I k and B k j. Okay, j, right? And where this k varies from 1 to n, right? Where n is the special number, which means which a multiplication conformance condition that the columns of A must be equal to the rows of B, right? So this makes our algorithm that every element of C ij will come from the multiplication of the ith row of A and jth column of B, right? So now you can set this one in a program that k every time will vary from 1 to n. So how I is going to vary, right? And how j is going to vary, right? So you will have in your program uh, three loops, right? There is going to be a loop for on the values of I. So there will be a loop for I, right? I will vary from 1 to m, right? Because I cannot vary, it is limited by the rows of A, right? And the j index will vary from 1 to p, right? Because the columns cannot be more than p, right? And you have the every time you have the calculation of Cij, which will come from the summation Aik Bkj, right? So J's are the columns of B, right? So that's going to be the structure of your program, right? Yes, that would be considered in the third loop. So it is going to be a three loop structure. So that was the problem I considered. The multiplication of two matrices. The sizes were m cross n and n cross p. So the I index would run from 1 to m and j index would run from 1 to p. So that's the algorithm for calculating the product of two matrices if they are consistent for matrix multiplication. So let's stop at this video at this point and take a deep breath. It calms the mind.